Welcome back, everyone, to our next lesson on chemical reactions. Today we're going to talk about double replacement reactions, the fourth type of reaction that we'll talk about in Unit 8. Although this type of reaction, double replacement reactions, are not considered redox reactions because we don't have an exchange of electrons between different species. So today we're going to focus on using Table F to determine a compound's solubility and being able to identify and write double replacement reactions. And by the end of this lesson, you should be able to do both. As I said, these are not quite redox reactions. They seem like they should be, but they aren't because they don't have an exchange of electrons between different species. Each species is not going to change its charge, so therefore they're not being reduced or oxidized. Now, double replacement reactions generally take place in water because ionic compounds will ionize there, and we can actually separate our cations from our anions in the water. So these reactions can actually occur because we do have a shift between ions from species to species, and that won't happen unless the particular ionic substance is dissolved in water, because we need those ions to be free from each other. So when we place a soluble compound or most ionic compounds in water, the molecule gets pulled apart by the polar water molecules. So if we think of something like sodium chloride, water is going to come in here with the negative end of water, and it's going to pull apart our positively charged sodium. The positive end of a water molecule is going to come and pull apart the chloride ions from the sodium chloride compound. These can now be dissolved, surrounded by other water molecules in proper orientation to keep them dissolved in solution. An insoluble ion will remain together. They can combine with other types of ions to form crystals and then drop to the bottom of the container, forming what we call a precipitate or a solid product. That wasn't there to begin with. We saw an example of this in class the other day. We want to start becoming familiar with Table F, which shows us different solubility guidelines for a few different types of solutions, which would contain different types of ions, some being soluble, some being insoluble. Sometimes this table is a little bit confusing to read, but it's almost like two different tables here. And in the left column of each of these, we have either insoluble compounds or soluble compounds. And to the right of that column in each table here, there are some exceptions. So for example, halides, our group 17 elements, will form soluble compounds. So if we combine chlorine, bromine, iodine, fluorine, any of these with another ion, another cation, then they would form a soluble compound, except when a halide is combined with one of these three: silver, lead 2+, or mercury. If one of the halides combines with one of those three, then it would form an insoluble compound. So this, under the exceptions, these would eventually, if they're combined, would become insoluble. And on the other side here, these would become soluble. We're going to do some practice with that. So we're going to do a little practice here with Table S. We'll do a few different examples with a few different compounds to determine whether or not they're soluble or insoluble, and being able to explain why. Take a second, think about this, try and name that compound. Pause the video and think about it. This is lithium carbonate, and it contains two different types of ions: lithium and carbonate. which has a charge of 2 minus. That's why we have 2 plus 1 lithiums combining with 1 carbonate ion. So we'll want to look for both of these in our table. I'm going to start with lithium. Lithium is listed here. It's a group 1 ion, and it's listed under the column that forms soluble compounds. And there are no exceptions. So no matter what lithium is combined with, it's going to form a soluble compound. We can look at this a second way. The carbonate ion forms an insoluble compound, except when it's combined with group 1 ions, which lithium is. So this would make carbonate soluble. So we can look at that in 2 different ways. Lithium carbonate is soluble. It's a group 1 ion, and group 1 ions are always soluble, no exceptions. Feel free to pause this video and try these before checking your answer. The name of this one is lead nitrate. It is lead 2 nitrate. So we have lead 2 plus, and we have nitrate minus 1. So we want to try and find these on here, a lead or a nitrate. And I see nitrate right here in table F. That's forming a soluble compound, and there are no exceptions. So any nitrate solution is going to be soluble. Another example, again, try and name, pause the video, and see if you can determine if this is soluble or insoluble. This is zinc chloride. So we try and find on here, we have a zinc 2 plus, and we have a chlorine minus 1. We'd like to try and find both on there. We have a halide, chlorine. Now chlorine is always soluble except when it's combined with one of these 3, silver, lead, or mercury. Since zinc is not one of those 3, zinc chloride is soluble. Again, zinc is not one of those exceptions, one of those 3 exceptions. Next one is copper carbonate. Copper 2 carbonate, we're left with a copper 2 plus and a carbonate 2 minus. I first see the carbonate here, and that forms an insoluble compound, but if we combine it with a group 1 or ammonium, then it would make it soluble. Copper is neither a group 1 ion or ammonium, so this has to be insoluble. Copper is not one of the exceptions to make a carbonate soluble. So at this point you should be able to determine whether a compound will precipitate out during a chemical reaction using table F. Onwards with double replacement reactions. So we'll look at the nitty-gritty of how these actually work. So the positive ion of one of our compounds is going to swap places with another ion, a negative ion, from the other compound. So we're going to start with 2 different compounds, and we're going to have basically both of our positive ions are going to switch spots with each other. That's why we get a double replacement, because 2 different species are swapping places with each other. And it takes the general form here. We can see C was combined with D, A was combined with B, and those 2 switch places. A comes to bond with D, and C comes to bond with B, and this is the general formula for this. So we have solution AB being mixed with solution CD. We have our cations that are going to swap positions with each other. Upon mixing these 2 solutions, AB and CD, the A ions are going to bond with the D ions, forming crystals of compound AD, and they will precipitate out of the solution. How can we identify that? Well, we have a solid designation here in our general equation. That solid tells us that AD is no longer soluble in the solution, otherwise it would have the AQ designation. So that solid tells us what the precipitate is. We could then determine from table F what the precipitate will be. So here's an example. We have two different compounds as reactants, two different compounds as products. Taking a look at the two products on table F, we got 1 and we got 2. To try and determine if these are soluble or not. Well, potassium is a group 1 ion, and that's always soluble, no exception. So this is going to get the aqueous designation. Nitrate is also always soluble, no exceptions. So that further proves to us that potassium nitrate is soluble, no exceptions. Chromate is listed as being insoluble with exceptions, but barium is not one of the exceptions. So barium does not make chromate soluble, so therefore barium chromate is going to be insoluble and does not dissolve, and that will form our precipitate and get our solid designation. Here's another example here, again starting with 2 compounds, ending with 2 compounds, and we watch our 2 cations swap places with each other. Calcium comes in bonds with the carbonate, sodium comes in bonds with the chlorine. Looking at these 2 here, trying to determine which one's going to be aqueous, which one's going to be a precipitate. Again, sodium is a group 1 ion, it's always soluble, no exceptions. Chlorine, or chloride in this case, is usually soluble. Sodium is not an exception to that solubility. Carbonate is listed as insoluble, but there are some exceptions that could make it soluble. But calcium is not one of those exceptions. That'll make calcium carbonate the precipitate because the components of that compound are insoluble and therefore would get the solid designation. Completing double replacement reactions. This will be done the same way redox reactions are completed, same way we did it last lesson. We're going to write the positive ion of the compound first, followed by the negative ion second. And we'll want to write the formula in such a way that we have the same numbers of atoms of each element on both sides of the equation. This is going to allow us to have a balanced reaction. We'll then use table F to identify what the precipitate is. So again, we're starting with 2 reactants, potassium chloride, silver nitrate, our reactant to form potassium nitrate, and something else. We don't know the phases of either of the other 2 products. We know that the missing compound is going to contain silver and chlorine because we have a potassium here, we have a potassium there, a nitrate here, and a nitrate here. We're missing the silver and we're missing the chlorine. So we know those are the 2 pieces that have to be there. No coefficient is given, therefore the formula is going to have to be AgCl. According to reference table F, potassium nitrate is soluble, no exceptions, and the AgCl is the insoluble precipitate, as silver is an exception to a chloride to make it insoluble. So this will get our solid designation, and the potassium nitrate will remain dissolved in solution. And we can finish our reaction. Another example, feel free to pause this and work out the problem. Determine your final product and the phases of each. So we have here 6 sodiums, 2 and 3, 6 sodiums, so that counts there. We have 6 nitrates. We have 2 and 3 here would be 6 nitrates, which means we're left with 3 magnesium and 2 phosphate. We use the coefficients in the reaction in order to determine that. Now, since we're not given a coefficient there, we're going to assume that we're just going to use the numbers that we're missing, and that'll count as our formula. We then have to determine which of these is soluble and insoluble. Sodium nitrate. Nitrates are always soluble. Phosphates are insoluble. Magnesium is not the exception. So magnesium phosphate is insoluble, therefore gets the solid designation. And sodium nitrate remains dissolved in solution. Spectator ions. Trying to identify spectator ions are a little bit different with double replacement reactions. They're just going to be the ones that remain dissolved in water as both a reactant and as a product. So we got to compare the aqueous designation across the reaction. And generally there are a couple here. So this solid is not there as a reactant, and that's silver and chlorine. So these can't be spectators. But the potassium nitrate does stay in the aqueous form on both sides. So potassium and nitrate will be the spectators in this reaction. Really, anything that doesn't form the precipitate is going to be a spectator. So at this point, you should be able to identify and write double replacement reactions. We will spend a fair amount of time practicing with this in class. Please bring to class any questions that you have. Hope everyone has a great day.